Okay, so good morning. This last lecture is on power amplifiers. Now, any op amp or any circuit for that matter, okay, will have something which will drive the external load. Okay. Now, you will see these small power amplifiers or driver amplifiers as they are called. Many times they are called as different names. Sometimes they are called as output stages. Sometimes they are called as driver amplifiers, or sometimes they are called as power amplifiers. Basically, depending on the amount of power that they give as output, some of these different terms may be used. Okay. Now, these power amplifiers are things that we encounter almost on a daily basis. For example, if you are listening to the lecture over your headphones, right, there is a power amplifier sitting there which is driving your headphones load. So if you remember, sometime back in our course, we talked about emitter followers and source followers, and I mentioned that emitter followers are good circuits which can drive resistive loads, right? Usually, I also gave the example of headphones or speakers and so on, and they are resistive loads, right? And their impedance will be, if you take like maybe around 100 ohms or something lesser, right? So the example of audio, right? So the load impedance can anywhere. So for some of the small speakers which you have probably in your car audio or home theater systems, or even for that matter, little bigger speakers and so on, they will range anywhere from 4 ohms to the professional ones are typically 8 ohms, okay, and pro audio is basically 8 ohms. You can sometimes put both in parallel and you'll get around 4 ohms or something. Consumer audio, earphones, things like that will range from something like 16 to around, like, let's say 150, 200 ohms. Okay, this is the impedance. Now the thing is, if you want to have, let's say, a 1 volt peak to peak swing. Oh, my voice is breaking. Uh,
Not very much, sir. You can continue.
Not very much.
No, sir, it's not.
Oh, it's okay. Okay. Probably I'm having some internet issues. I'm not sure. Okay. Just let me know, guys, in case it happens. I can repeat some portions. Okay. So, for example, if you have a 1 volt peak to peak swing, and let's say this is across at RL of, let's say, 10 ohm. Okay. Now, what is the current peak to peak swing that we need? 1 by 10, it is 0.1 ampere peak to peak, right? That is 100 milliamperes, which is quite large. Okay. Now, if you look at some of your audio systems, let's say your home theaters and all, it will be in the range. Okay, this is a 100-watt system or a 200-watt system, and so on. Now, if you take, let's say, if something is, let's say the power is, let's say 100 watts, right? This, if you give a sinusoidal signal, okay, that is easier for us to measure and do analysis. So Vrms squared by 2RL is 100 watts. Okay, let's say RL again is let's say a 8 ohm speaker. Okay, a professional 8 ohm speaker. So what is your Vrms squared, or rather what is your Vrms? Basically it is 100 into 2 into 8 ohm, and root of this, basically it is 40 volt. So if you want 100 watts of output power from your 8 ohm speaker, right, and if you're giving a sinusoid, basically your RMS voltage is 40 volt. Okay, and your IRMS basically is in the order of what, 5 ampere, right? So we need circuits which can handle these large amounts of currents and voltages. Okay, so the BJTs that you used in lab, they are actually low voltage BJTs. Probably they can handle up to 15 volt, 15 volt or something like that. Okay, there are also other devices called power transistors. Okay, in fact, I think for one of your experiments, when you had to drive a 64 ohm load or something, you would have used one of those smaller power transistors. Of course, it is not too much. I think its maximum maximum power that it can handle, I think it's around 800 milliwatt or little less than a watt. Okay, there are other power transistors which are much larger, okay, and can handle much higher voltages and currents. Okay, so in case some of you have opened up your audio amplifier or your home theater, or maybe your old cassette players or CD players or something, like you would have seen some of these bigger transistors with a heat sink. Okay, you would have seen heat sinks, right? Some kind of a metal cap. In fact, if you have at some point of time, looked at some professional amplifiers or something which they use, let's say for public address system and so on, right? You will see that they will have very good kind of thermal things. Like sometimes they'll have some fin type structures where which can cool these transistors. And if you open them, you'll see there will be a big transistor with a big metal cap, which will be cooled by these vents and so on, right? And if you have touched some of these big amplifiers which they use for, let's say, big public address meetings and so on, it will be very hot. Okay, that's because the power dissipation is quite significant, and these power transistors are the ones which do the job. Okay, so today we are going to look at such types of things. Of course, this can be scaled. It can be something which is delivering some milliwatt of power to your headphones. It can also be stuff which is much higher, which is delivering power to your, let's say, home theater systems, or for that matter some big audio systems which you use in public address systems or in concerts or in theaters and so on. Okay, so of course things get scaled. You use appropriate transistors for all these things, but now we are going to look at more of the fundamentals of those things. Okay, now let us start with what is a basic emitter follower, right? And this is something which can be used as the output state, as I mentioned earlier, right? Let's say this is your V in, and what you do is basically you have, let's say, let's use bipolar supplies because that's how most of these things work. Minus VEE, some I naught is there, and you have your RL. Okay, so typically when you have bipolar supplies, it's easier to bias this whole thing such that the DC bias here is 0 volt. Okay, and you can deliver your RF, your AC current, right? Now this, how do you implement this current source? You can basically put another transistor which is appropriately biased. Let's say some VB is there. This is our V in. Let's say this is going to plus VCC. Yeah, I have started the recording. Let's say this is going to minus
So the
VEE.
capacitor should be there, right?
Sorry? Capacitor.
Sir, across the load, yes, sir.
So you're talking about a capacitor here. Yeah, many times it is done. Okay. So for right now, for our analysis, we'll kind of assume that it is already there. Okay. Or you can also, as I mentioned, you can also get rid of it by kind of there are certain circuit architectures where you can do certain things to get rid of this capacitor. Okay, because one thing is like you can bias it and do certain interesting things here, such that the DC voltage is always 0 there. Okay, so DC current does not flow through the load. Okay, you can maybe add some additional circuitry which can do that. Is all that is also quite routinely done, because sometimes what happens is when you talk about very large currents and very large swings, these capacitors which you put for DC blocks, okay, they can become non-linear. Okay, which is their capacitance value becomes a function of the voltage or the current flowing through them, and so that produces distortion in your audio signal and so on. So there are cases where you use capacitors, and there are also cases where you don't use capacitors. Okay. So right now for our analysis, just ignore the capacitor for now. We just assume that there is no DC current flowing through. Okay. All right. Anyway, this is not a circuit that you will anyway end up being using. We will look at the other improvements. Okay. All right. So here, so this is how our common collector or our emitter follower looks like. The job of Q2 is just to ensure that a current of I naught is flowing here. Okay. Now, what is the maximum V out that this can reach? Vout max basically can be VCC minus VCE sat of 1. Okay, this is the maximum that this Vout can reach, right? So in that case, what is the amount of current that is flowing through Q1? Let's say I1 is the, let's say this is IL, let's say this is anyway fixed, this is I0. The amount of current I1 basically now has to be I0 plus IL, right? And IL is basically given by Vout max by RL. So you can see that now there's a very large amount of current which is being conducted by this transistor Q1. Now what is the Vout min here? Vout min can come due to two different things. If it can be either minus I0 times RL, right? That is to say that Q1 is pretty much off and like, all the current basically is flowing like this, right? So I0 is minus I0 times RL, or if you choose I0 in such a way, then what can happen is it can reach down to minus VEE, right? So basically it can come down to minus VEE plus VCE to SAT, right? This can be the thing. So either of the thing. So it can either be that your I0 is limiting, or it can be that if your I0 is not limiting you, you can come all the way down to your almost close to your negative supply rates. So for this condition to happen, what should happen? I0 should be greater than or equal to, let's say, modulus of minus VEE plus VCE to SAT divided by RL. Now, if this condition is satisfied, then this second expression will work, right? So you can basically draw the transfer curve, right? Or let's say this is your Vin and this is your Vout, right? You can say that this is going to be, let me use another color, going to be something like this. The max being VCC minus VCE sat. In case your RL, your I0 is not satisfying this condition, it will become minus I0 times RL, or it can go all the way down to minus VEE plus VCE to SAT. Okay. Now this is how your amplifier works. This type of an amplifier is what is called as a class A amplifier. Okay. Why is it called as a class A amplifier? So let us look at some of the voltage and current waveforms, right? What is the amount of current that is flowing through I1? If you look at I1, let's plot I1. Straight lines are tough. Let's say this is across time. First, let me draw the input signal. Let's say this is my Vin. Okay. Now our IC1, how will our IC1 behave? Let me just make it smaller so that I have space. IC1, that is the current flowing through this transistor, right? When it is going to max, what will happen? Basically, it is going to support I0 plus VCC, almost close to VCC by RL, right? And when it is, if you say that this equality is achieved, right? If this equation is achieved, and let's say, let's put some assumptions. Let's say VCC is equal to magnitude of VEE, right? If let's say it's plus or minus 15 volt, plus or minus 12 volt, okay? And let's say I0 is chosen such that it is equal to VCC or VEE minus VE plus VCE sat by RL, right? If you choose things to be like that, when there is no signal, this will be conducting I0, right? As the signal increases, basically what will happen? it will become I naught, you can approximate to be what? VCC by RL. So this will become 2 VCC by RL approximately, and then it will go all the way down to 0 amps when it is at this point. Okay, we are looking at the extreme, that is like we are using the amplifier completely to the max power possible, right? So when you are using it to the max power possible, if let's say your Vout is reaching up to VCC minus VCE set, approximately you can say that the amount of current that is flowing is 2 times VCC by RL if this condition is satisfied. Okay, so it reaches a maximum of 2 times VCC by RL and goes down to 0. Okay, and when there is no input signal, when your input signal is 0, then IC1 is basically equal to I naught. Okay, now of course the Vout basically will follow like this. So this can be VCC minus VCE sat, right, and this will be minus VEE plus VCE sat. Okay, this is your Vout. Of course, your IL, if you plot your IL, let me plot using a different color, right? IL will be what? IL will be 0 when there is no input, correct? Oops, where did it go? Yeah, and it is going to reach, let me say, IL max, right? IL max being VCC by RL, and this is minus VCC by RL. IL is going to be centered at 0, but whereas the quiescent current which is flowing through your transistor Q1, there is going to be always I naught flowing even in the absence of signal. So let us compute what is called as efficiency. Okay. Efficiency is given by power delivered to the load divided by power drawn from the supply into 100. Okay. So efficiency is typically in terms of percentage. So now let us try to write what is the power delivered. What is the power delivered to the load? It is half V naught squared, V naught hat squared by RL, where V naught is the RMS, sorry, this is the, I think I made a mistake here, I'm sorry, I'm just going back. It is V RMS squared by RL, so this will be, I think, even higher, so please make that change. So it is V naught squared, V naught is the max, or rather let me say the amplitude of output. Let's say it's the max amplitude of the output. Okay, so right now we are trying to measure what is the max efficiency. What is the maximum efficiency? For that we are going to the condition where you have the maximum power delivered to the load, and let's see what is the power drawn from the supply. Okay, now if you look at this, is the numerator you have drawn here, written here, right? Yeah, I am recording. V naught squared by 2 RL, right? Where V naught is the max amplitude of the output, and V naught hat can be written as what? Approximately VCC by approximately VCC. Correct? What is the power drawn from the supply? It is basically I naught into VCC plus modulus of VE. Correct? In other words, you basically have 2 times VCC. If VCC is equal to minus VE, as we have seen earlier, this basically becomes half VCC squared by RL into 1 divided by 2 times VCC times I naught. And we saw that I naught is given as approximately VCC by RL, such that it can hit the bottom rails. So this can be written as what? Into VCC into RL. Right? Now what do you get? You basically get 1 by 4. So your max efficiency into 100, which is basically what? 25%. The reason we took I naught, so here if you see that although there is a sinusoidal signal, the current drawn from the supply, right? Here, although it is a sinusoidal signal, basically it averages out over time, and therefore the average value can be taken as I naught. Okay. So what we have seen here is, if you talk about the power delivered to the load and the power drawn from the supply, if you take the ratio for the peak output power case, what is your max efficiency? It is only 25%. Okay. In other words, if we use class A amplifier, okay, to deliver 100 watts of power, we need to draw 400 watts of power from supply. Okay. This is a colossal waste of power. Okay. For smaller things like, for smaller output powers, this is still okay. But when you are talking about larger output powers like how I gave, you have to draw a very large amount of power. And what not only is it that your power bills go up, it also means that your components need to handle large currents. Okay, so the cost of everything goes up. Okay, so and also please understand that this is the max efficiency. So typically, if you plot efficiency versus input voltage, it will look something like this. It will go linearly kind of, and then it will saturate at this one. Okay, this is 25%. So if you play some audio signal, the efficiency, the average efficiency will be much lesser than 25%. So the biggest, so we need to find out a circuit or some other topology which will give us much more efficient delivery of power. Okay, we need something which will help us with that. Now the first thing to notice here is, the biggest culprit is that you have this I naught flowing all the time. Okay, the biggest problem is I naught is drawn from the supply even in the absence of signal. Okay, so we need to do something to make sure that this does not happen. Okay, so that is where people came up with this class B amplifier. Okay, so the class B amplifier is all let me just draw it. So this is what is called as a class B push-pull amplifier. I'll explain these terms, why they are called so. Okay, you have, of course, we know that emitter followers are the ones which help us, right? So what I'm going to do is, I'm not going to bias this transistor. Okay, I want this transistor to conduct only in the positive half cycle. Okay. All right. My input is given to this transistor Q1, which is an NPN transistor, and this transistor will conduct only in the positive half cycle. Now to take care of the negative half cycle, I am going to put another complementary transistor, which is a PNP, right? This is minus VEE, and this Q2 will take care of my negative half cycle. Okay. This is a very rudimentary class B power amplifier. Okay, this is what is called as a class B push-pull stage. The reason why it is called as a push-pull is because in one phase the transistor is pushing current into the load, and in the other phase Q2 is, you can kind of think of, pulling the current. So it is basically like, in one half cycle one transistor does some work, and the other half cycle the other transistor does some work. So this is why it is called as a push-pull amplifier. Okay, so both Q1 and Q2, so let's just put it, Q1 and Q2 are not on at the same time. So Q1 takes care of the positive half cycle, and Q2 takes care of the negative half cycle. Okay. Now, and the other important thing is there is no power consumption when Vin is 0. That is when you don't have any input signal, right? There is 0 DC power consumption. Okay, both Q1 and Q2 are off. Both of them do not conduct, and therefore there is no power drawn from the supply. Okay, so let us try to draw some waveform. Just keep this circuit in mind. Let's say this is going to be my input Vn. Let's say this is my input, or let me just draw it a little. Okay, this is too much. Okay. Okay. Let's just stop with this, and let us look at the output. Now, many of you might come back and say the output till the input crosses this VBE, which is nominally, let's say, around 0.7, this transistor Q1 is not going to conduct and Q2 is also off, right? And therefore, oops, let me say my V out till it reaches, let's say this is 0.7, till it reaches 0.7, there is no output. After that, what is going to happen is it's going to act as an emitter follower. Same way, let's say this is plus or minus 0.7. This is going to come back to 0 by this time, right? And my second transistor Q2 is going to start conducting only after this reaches minus 0.7, right? Okay, and then again Q1 is going to conduct only in the positive half cycle. Okay, so my output waveform is basically going to look like this. I took the example of 0.7 for power transistors and so on. This may not be the case. It can be a little higher also. Okay, sometimes it can be 1 volt, 1.1 volt, and things like this, right? So I'm just taking an example. Let's just call it VBE. In this example, I've taken 0.7. Okay, it can differ from transistor model to transistor model depending on which model of transistor you're using, depending on the output power that is required. Okay, so now if you look at the output signal, you see that this is no longer a sine wave. It's no longer a proper sine wave. Okay, it has some unwanted characteristics. Okay, and this particular region, okay, where the output voltage is 0 when it is not supposed to be, this is what is called as crossover distortion. Okay. There's this term used called as crossover distortion, and in class B amplifiers, crossover distortion is a problem. Okay, and same way, if you want to look at the current that is flowing, let's say the IL will also basically follow the same thing. And so on. Okay, so this crossover distortion is a major problem in class B amplifiers. Okay, but before we move over and look at what improvements can be made to this class B amplifier, let's try to find out how is the efficiency of this particular circuit. Okay, so let us try to derive that, right? So efficiency is basically what? Power delivered to the load divided by power delivered to DC, right? What is the power delivered to the load? So let us write this. Power delivered to the load again is V naught cap squared by RL. Okay, V naught cap is basically your max output amplitude. Okay, so for our derivation here, let's just say it is approximately taken to be VCC. All right. Exactly, it can go up to V naught minus that VCE sat, but I mean VCC minus that VCE sat, but VCE sat will be typically around what, 0.2, 0.3, and then this is, let's say, 15 volt or 20 volt, or sometimes if you are trying to deliver much higher power, it will be like 100 volt supply or something. So that is literally nothing. Okay. Now what about PDC? Now how is the current? I said that this is the current which is drawn from the supply to the load. If you draw the current which is drawn from the supply I VCC, okay, let me just say ICC being the current which is drawn from the supply, basically that is also going to be like this, right? ICC is going to be like this, only the positive half cycle, right? And what about IEE, the current which is drawn from the negative cycle? It is going to be like this, and then it follows only the negative half cycle. Okay, so the current waveforms are a little different. So I think you haven't studied about Fourier analysis yet. I think, have you studied Fourier analysis, Fourier series?
Yes, sir. Doctor.
Yes or no?
Yes, sir.
Yes, sir.
Yes. Okay. So you can basically, this is a periodic. This is a periodic waveform. You can use it. You can expand the Fourier series for it. So if you approximate this to be, you know, a half wave rectified sine wave, you will basically get the Fourier coefficient for DC. So this type of a waveform, I think you might have already done the Fourier expansion. So you will have what? A naught plus, you know, summation of AI for, you know, different cos omega, I omega, let's say A n cos n omega, n omega naught t, and n can range from 1 to infinity, plus some summation of bn sine omega n omega naught t, n ranging from 1 to infinity, right? Now what we are interested in the D is in the DC power. Okay, so what is the DC power here, which is basically A naught? So you can do the Fourier expansion and you will see that it is basically equal to, this A naught component will be basically 1 over pi times VCC by RL. Okay, the current waveform, the peak is basically VCC by RL, the current drawn from the thing is VCC by RL. So if you do the Fourier expansion, the power drawn from VCC is this much, and the power drawn from VEE is also this much, right? And therefore the total DC power can be taken as 2 by pi VCC by RL. Again we are saying that VCC is equal to minus VEE, right? So this is your DC power. So let us compute your efficiency. So your efficiency here now becomes half VCC squared by RL into 2 VCC at the bottom. It becomes pi times RL. So basically what will you get? Did I miss something somewhere? Yeah, sorry, this into VCC, this is the current, right? So basically it becomes 2 VCC squared by RL, right? So now the efficiency basically becomes pi by 2 into 100. So this basically efficiency is 78.5%. Again, let's say this is the max efficiency that we are calculating. If you take this, basically you will get, I think you'll have pi by 4, sorry. Yeah, you'll have pi by 4. So if you take what is pi by 4, 3.14 by 4, you will basically get 78.5%. So now we have seen that by this improvement or this circuit technique that we have introduced, this class AB amplifier has, this class B amplifier has improved your efficiency from max efficiency from 25% to all the way to 78.5%. Okay. Now you can calculate this is the max efficiency. Now you can calculate it for other values of output voltage also. We don't have time to do that, but you can see that as V out or goes like this, the efficiency basically will kind of go a little quadratically and then go up, okay, and reach 78.5%. Now this is how it basically works. But again, the disadvantage is that it has this crossover distortion. Okay. Now how to solve this problem? How to solve the crossover distortion problem? Which is where we come up with this another class of power amplifiers called class AB. Okay. Now here in class A, we can say that Q1 was conducting for all cycles, or in other words, for 360 degrees of the input phase. Right? That is to say, when you I'm just going back to the class A power amplifier. Here you can see that Q1 is basically conducting for the entire cycle of the sine wave. Okay, for the entire 360 degrees of your sine phase, it is basically conducting, right? Whereas in class B, you see that Q1 or Q2 is conducting for only 180 degree of the input signal. Let me just say input, right? This is the characteristics of class B. So only for one half cycle, I mentioned it as one half cycle, you can say that a phase of 180 degrees only it conducts. So that is how class B is defined. Now when you talk about class AB, we say that the class AB conducts for more than 180 degrees. Okay, but it is definitely less than 360 degrees. It is somewhere between class A and class B, but very closer to class B. Okay. Now you might say the solution to this crossover distortion is basically if you can add some voltage, right? Let's say if our circuit can be modified to something like this. What have we done here? We have just added some, let's say some VBE here, right? Just some potential which is enough to put the transistor at the edge of turning on, okay, so that when the signal comes, it is on, right? Same thing for the PNP transistor, right? Both Q1 and Q2 are just basically put at the cut-in voltage or just at the threshold of turning on, okay. But of course we know that even before this cut-in voltage, there's a small amount of current which is flowing, right? And when the signal comes, it basically conducts. This is basically what is called as a class AB amplifier, and this basically solves the problem of crossover distortion. Okay. Now the question is how to come up with these two voltage sources or these two batteries, VBE and VEB. Okay. You can't say, okay, I'm going to put a battery for everything. That is not a possible, feasible thing, right? And batteries also come in very fixed voltages. So one simple way to do it is basically, let's say we make use of diodes. So the way in which this is done is there is some bias current which is flowing, and what we are doing here is something like this. Yeah. Now what is happening basically is that we are putting this PNP transistor in the usual mode, okay, in the usual class AB mode, that is it does not conduct till minus 0.7 or minus VEB, right? But on the other hand, we are giving two diode drops to this NPN transistor Q1, okay, so that the NPN transistor is going to, if we look at the waveforms, right, let me just quickly draw the waveforms, right. If this is your input signal, right, the Q1 is going to conduct for little more than 180 degrees. If this is the thing, it is going to conduct for little more than 180 degrees, right? This is how it is going to look like. Let's say this is IC1, and let us also look at IC2. IC2, basically what is IC2 going to look like? It is going to be, where this is going to stop, that is where it is going to take over, right? Where, this Q1 is going to stop, that is where Q2 is going to take over. Okay, so here you can see that the conduction angle, okay, whatever I said here is what is called as conduction angle, right? The conduction angle is now, you can see, greater than 180 degrees for this Q1, but it is definitely far lower than 360 degrees. This is what is called as a class AB power amplifier. Okay. Now there are more variants to these things. There are other things that can be that are usually done, and how to do those things. Of course, I don't have time to go through all the circuits, but I'll just add one or two more features. Okay. Now we have come up with a circuit which is now working fine. Of course, the efficiency now will be a little lower than the max efficiency will be lower than 78.5%, and we can say that even for the property of class AB is that, let me write it here, even for for V in 0, a small quiescent current flows. Okay, so the efficiency will be of AB will be lesser than efficiency of class B. All right. Now let us add two more features to it. How to solve thermal runaway problem. Okay. What is thermal runaway problem? We saw that this is there for the BJT transistors. Like as temperature increases, current increases, IC increases, which will cause temperature to increase even further. Okay, so this becomes a positive cycle, just keeps increasing, and then ends up with the transistor burning out. Okay, so we need to somehow limit it. Now, how will we limit it? Basically, we will limit it by putting some feedback, right? How did we do thermal stabilization of BJT? By putting an emitter resistor. Here the problem is, if you put an emitter resistor, a larger value of emitter resistor, you will end up with more loss, right? Because you want all the power to go to the load. Okay, so you put a very small emitter resistor, maybe in the order of maybe 1 ohm, typically 1 or 2 ohms resistor. Okay, same way you put RE around 1 ohm, and this is your input. Of course, let's say here we will have some biasing network, because now that you have put your so there is the circuit called as VBE multiplier, so I will not go into it, but let's just say there is some biasing network which basically makes sure that the bias is done properly. Okay, so we'll not go into it. You can check it in the book. There is a circuit called as VBE multiplier. There are other schemes also. Okay, a very easy way to do it is basically to say that I will put a current source, and then sometimes maybe just put a tunable resistor, right, and put a V in here. Okay, now this tunable resistor can be adjusted to make sure that these RE drops are taken into account. Okay, because now your VBE, the base voltage has to be taken a little higher than just a VBE. So that is done by using this tunable resistor or by using certain other methods. Okay, So this is the way to solve thermal runaway problem, or basically it makes sure that if there is increase in temperature and increase in current, it stabilizes. This particular circuit thus provides thermal stability. Okay. Now let us also see one more way to do things. Right? There is also one more thing that people do, which is basically that if you have a transistor like this, right, you can do short circuit protection. Okay, let us include short circuit protection. What is the short circuit protection? Suppose you are supposed to have a certain load impedance RL. Okay, by mistake, let's say you are connecting your speaker to your amplifier, and by mistake you touch both leads of the wire. Okay, you are creating a short unintentionally. Now if you don't have the short circuit protection, what will happen? Your amplifier will burn, because you are going to take a much larger amount of current and it will destroy your amplifier. So a simple mistake by just touching the two leads of wire which is going to your speaker is enough to ruin your DVD player or your home theater. So of course people do put this short circuit protection, and the way it is done is very simple. Okay, what you do is you put a small BJT. Okay, and the BJT and this resistor RE is also designed in such a way that this transistor, let's say Q3, this is Q1, I'm just drawing it only on one side. Okay, this Q3 turns on when, let's say, IL times RE exceeds 0.7 volt. Right? Now when this turns on, what will happen? This is basically going to short Q1 base. Basically it is going to turn off Q1. Right? Because now when you turn on this Q3, this Q3 acts in the saturation region. It acts as a switch, and it is basically going to short your Q1, and it is going to limit the current. Basically there will be some small amount of current flowing through RE, but now it is making your base voltage come even lower than your emitter voltage, and that way it is going to shut down this transistor Q1, thereby providing short circuit protection. Okay, now what is the current at which this short circuit protection has to kick in? That you have to decide by basically designing your value of RE. Okay, so this is the way that short circuit protection is there in almost all power amplifiers. This is a very essential thing. Okay, and there are other ways of biasing these two this NPN and PNP transistors. Okay, another option can be by using two emitter followers. Okay, so you can put an emitter follower here at the base of Q1, another emitter follower at the base of Q2, such that you can adjust the DC bias appropriately, and you will be able to take care of thermal runaway problem. You can take care of short circuit problem as well. Okay, lastly, let me just talk about this concept of, for all these different transistors, we use what is called as a Darlington configuration. Okay, in fact you will see this Darlington pairs or Darlington configuration being used for very high current applications. Okay, what is the Darlington configuration? Basically you take two transistors, okay, and you connect them like this. What have we done here? Here you have taken, let's say this is your base, this is your collector, this is your emitter. Now what is happening is IB2 is given as what? Beta plus 1 times IB1, and therefore the total collector current here, IC2, is going to be what? Let's say this has a beta 1, this has beta 2. The total collector current IC can be written as what? Approximately beta 1 times beta 2 times IB. Okay, basically you are having beta multiplication with these Darlington pairs. The same thing can be done for PNP transistors also. Okay, So here what happens is you have this and you have this feeding into this one. Okay, so you can have Darling configuration of NPN transistors, or you can also have the Darlington configuration of your PNP transistors. Okay, so these transistors are used very commonly. PNP version also possible. So basically your base current here goes as the, okay, this is what becomes, this is your emitter, this is your collector, this is your base. So these are used for power transistors. Okay, so with this we complete our syllabus. Okay, so I have also uploaded one more lecture yesterday. So lecture 26 and 28. Okay, those are recorded lectures. Please do take the time to go through them, and all these are quite important concepts. And we will be, you will be tested on the conceptual things. You will be tested on the basic concepts of these topics in your final exam also. Okay. So with this we complete our portion for my part of analog electronics. Is there any? Yes, of course I'll be asking these things in exam. Okay. So all these lectures, whatever I have taught till now, including the recorded lectures, are included for the exam. So please take time to go through them and understand them in detail. Okay, these are important concepts. Of course, we had to rush quite a bit, but please, since you have the recorded lectures, you have the opportunity to go through them at your own pace, and you can refer to the textbook also. I'll try to send some practice problems or practice assignment today, and you can use them. Okay. Anyway, so thank you very much. It was a nice experience teaching you all. Although we had to do it entirely online for this semester, I enjoyed the interaction that your class provided, and I hope you have learned quite a bit in both network analysis and in analog electronics in our teaching. Okay, so all the best for your exams, and thank you.
Sir,
Thank you, sir.
thank you, sir.
Thank you.
Thank you, sir.
Sir,
Yeah.
sir, do you have any idea whether next time will be online or offline?
As of now, from what I can predict, I think a good part of next semester will also be online. Okay, so we don't know how things are going to change, but still, even the project students, the final year project students for both MTech and BTech have not yet arrived in campus. So they are slowly arriving. So it's only after they come, then maybe PG students and then UG students. So I think either entirely or maybe the first 3 months or so definitely will be online.
Okay.
Okay, so thanks everyone. Yeah.
Okay.
Have a nice day.
Thank you, sir.
Yeah.